Starting where we left off in the previous video, I'll be talking about the MPPT controller. This MPPT controller uses incremental conductance to adjust the pulse to the switch in the boost converter, the IGBT. And for this application where we have a 500 volt output from this array here, you're looking at around 0.5 for the duty cycle, somewhere around there, to get the appropriate voltage boost. And this is calculated with the equation for the duty cycle for a boost converter. And we can dive into the algorithm now. So here we have the algorithm, the incremental conductance algorithm, to essentially adjust the duty cycle as the current and voltage is periodically tested throughout the simulation. And so up here in the top half, we have the portion that finds the dI over dV value. And so we have two inputs. We have our current from the PV array and our voltage from the PV array. These blocks take the magnitude and the phase. These are Fourier blocks, and they'll take those aspects of the signal. The magnitudes will be divided I over V, and then the phases will be combined, and then through a trigonometric process will be multiplied by that I over V calculation over here, and it will produce the dI over dV signal. Now over here, this is the second part of this initial increment, this initial algorithm step. We have these mean blocks. They are finding the current mean and the voltage mean, with this block producing a limit on the voltage. Then again, we're getting an I over V calculation here, and this dI dV signal and the I over V signal are fed to this summation block where they are added together. That summed signal was then sent to a conditional block where it is tested to see whether the signal is less than 0, equal to 0, or greater than 0. If the signal is equal to 0, nothing changes. The duty cycle is appropriate, it's producing the right output voltage, and nothing needs to change. If the signal is greater than 0, the duty cycle will need to decrease, and that will be adjusted in the next testing cycle. If the signal is greater than 0, or sorry, less than 0, the duty cycle will need to be increased. And then over here we have some components that act as the integral regulator, which will regulate aspects of the duty cycle. Now if we zoom out a little bit, we can see that the duty cycle that was being calculated in the MPPT algorithm was actually the change in duty cycle. And this change, so this delta D value, is added to an initial duty cycle value, added or subtracted, and with the limit of that signal being 1, and then it's sent to a pulse generator, which creates a pulse for this switch. Now we have a similar process that happens over here for the 3-level voltage source controlled converter, voltage source converter, where you have an algorithm controlling the switching operation of the converter. The specifications of this converter were a little odd in that there was no voltage drop specified, kind of like in the boost converter with the diode and the switch. But it may have been accounted for in the internal resistance. The signal from this inverter is then sent to this filter between the inductor and the capacitor. These make up a filter that filters out the harmonics in the AC signal. And if we take a look at that output, we get a pretty nice sine wave that goes up to almost 400 volts. If we go back here, and so that produces a voltage that is, and that was the voltage after the filter. And